What kind of color? What's your favorite color? Pink? Red? Looks like a nice blue color we're getting here. Okay? This universal indicator is telling me that the pH of this is basic. Okay? It is a high pH. What I'm going to do now is I'm going to add an acid. See the nice color? I need my acid. So what happens if I add an acid to a base? Does anybody know? I get neutralization. Okay. The acid has hydrogen ions. The base has hydroxide. I'm going to get a neutralization reaction. Let's see what we'll see here. Anybody know what this is?
Dry ice.
Dry ice. Is it an acid?
No, it's cool.
No, it's a solid, and solid carbon dioxide. But when you put it in water, what happens? So what's happening here? The CO2 is producing acid when it reacts in water, produce carbonic acid. Carbonic acid will react with the hydroxide from the base, and we'll go through the different colors of spectrums as the pH changes. Okay, so you saw the blue, right? That's the basic. Then you see the green, that's neutral. Now we're seeing yellow, orange, so that means acidic. Okay, so now we have an acid here. And this is, why do we get all this smoke here? What is that for? Anybody know? That's the gas, right. The CO2 is subliming. We get the gas coming out. Some of it's coming out of the solution. Some of it dissolves in the water. Okay. Let's try to turn it back. See what happens if we add a little bit of hydroxide back here. I think I added a big piece of pour in it. I gotta be careful. Woo!
Wow.
Wow.
It's really turning back to acid.
I want to go back to my blue. I'm getting there. Why does it keep changing colors? Because it's still dissolving, right?
How long will it continue to change color?
Until the base is equal.
How long? You can tell right now. I can tell you how long it will.
Until the ice
That's right. Until there's no more solid CO2 to shift the equilibrium. All you're doing is shifting it back and forth.
Okay. I don't think it's going to hold over.
No, I think you're good.
So we're going to see the different colors here.
Let me ask you another question. Look at the air around you. What is he, some kind of nut? Okay. What color is it? Colorless. What's the stuff coming out the top? CO2. What color is it? White. Why is it white there and colorless here? Nice work. Thank you.
Ladies and gentlemen, the dry ice you just witnessed. Wait a minute.
We should point out that in order to leave, there is a quiz at the end of this show. 10 questions on the demonstrations and the questions I ask. You need a 9.5. It's a 10-point quiz to leave. Otherwise, you're forced to stay after school.
Hey, ladies and gentlemen, the dry ice you just witnessed sublimes at negative 78 degrees Celsius. It's pretty darn cold. We're going to go into the down outright Arctic now. In this flask, this is called a Dewar flask. It's basically a fancy thermos, except they charge you $500 for it. And it is designed to handle extremely cold liquids. And here we have liquid nitrogen. Now, roughly 78% of what you're breathing in right now, the composition of air, is nitrogen. Your body doesn't do anything with it, you just exhale it right back out. But if you cool nitrogen down to negative 196 Celsius. That's 77 Kelvin, which is about as close to absolute zero as I ever want to get. Nitrogen will condense into a liquid. So I'd like to do a couple of liquid nitrogen demonstrations for you, but first I'd like to show you what it looks like. So we're going to pour it right out into this beaker. Thank you. Okay, liquid nitrogen. And what is that liquid nitrogen doing? Okay, oh, it's definitely smoking, no smoking. What else is it doing? What do you see? Somebody said it, boiling. Okay, this room is piping hot compared to the liquid nitrogen, and it boils at negative 196 Celsius. And since temperature remains constant during phase change, I'm pretty confident we're at negative 196 degrees Celsius. Now the nice thing about liquid nitrogen is you can do all sorts of cool demos, get it? Cool, get it? That you can't normally do at room temperature. So, what do we got? For you. So, ladies and gentlemen, we have flowers. Now, our flowers have some physical properties. Name one physical property of the flower. Red. Good, we got color.
Very soft.
Soft and
Smells good.
it's got an odor. Okay, now the question is, how will placing this in liquid nitrogen affect those physical properties? Will it still be red? Will it still be soft? Will it still have an odor? Well, let's find out. Okay, it'll take just a few seconds for it to chill out. Get it? Chill out. Well, our flower is still red. I really don't want to sniff it to see if it has an odor, but definitely not soft anymore. For you. So, you saw what happened when you put a flower in liquid nitrogen. Let's put a whole bunch of other things in liquid nitrogen. See what happens.
Let me ask you another question. This is now liquid nitrogen. What color is the smoke here? White. So CO2 as a form of smoke is white, and so is the liquid nitrogen white. Why?
This is like crazy Russian. I bet he's gonna take the ball and he's gonna like crunch it.
All right, so I just put a whole bunch of things in liquid nitrogen. One of them's brand new. I've never done this one before. That's the big leaf. That's called a collard green. And so my question to you is, how will the physical properties change of that leaf as they place it in the liquid nitrogen and take it out?
It's gonna hurt it. It's gonna freeze.
Any ideas?
It's not gonna smell like it.
Let's find out. Now the leaf should be ready first. So we'll take that out and we'll... That wasn't any good. Oh, a handball. Now you saw me bouncing the handball earlier. So a handball is both round, blue, and it's bouncy. Oh yeah, I'll need that, thanks. Okay, so my question is, will the handball still be round when I take it out?
Probably not. I'm gonna say yeah.
Will it still be blue?
Yeah. I'm gonna be confident.
Will it still be bouncy? No. You have little faith. You want to get out of there.
Oh, nothing happens. you open the freezer?
I'm a righty. So, our handball appears to still be blue. It appears to still be round. But if we try to bounce it, not so bouncy. Not so bouncy. I also put a banana in here. Question, is it still a banana? So what type of change are we wanting? Physical or chemical? Well, it's still a banana, it's still made of the same stuff. It's a physical change. So you guys deal with this all the time. You probably have this thing in your house, it's a rectangle, you put food in it. Right, and one portion is a freezer. We're basically doing the same thing. Maybe, maybe not. We're basically doing the same thing. Basically doing the same thing to the banana, except this is frozen so solid and so hard that we can now use it as a hammer to hammer a nail into a piece of wood.
Is that still edible?